Welcome to Design Your Solar Roof. I wrote this program to put architects, engineers, contractors, and solar field installers behind the desk of a solar designer. Learn basic project fundamentals while also learning advanced design and installation techniques. My name's John Cromer. I've worked in the solar industry for 10 years. I'm a mechanical engineer by degree. I've also passed the Master Electrician exam and Residential Builder exam in the state of Mississippi, as well as a private industry certification program called NABCEP. Our program outline today is pretty robust, so we're going to get started right away. But in this program, we'll be covering everything you need to know to evaluate the preliminary design process of a rooftop solar array. So we'll be covering performance estimation, economic calculations, array layouts, site assessment techniques, shade analysis, um, sizing the inverter to get the relationship right between the array and the output capacity, different interconnection strategies based on service panel amperage. We'll also show how computer-assisted design promotes the generation of project documentation, as well as some final design and permit documentation techniques. We'll talk about racking sizing, which should give you enough skill to complete a specialty balance of system material between the modules, inverters, and racking. We'll discuss aesthetic considerations to keep your array looking good. We'll talk about some advanced installation techniques called internal conduit runs, which I think are particularly important on residential arrays, but have some merit on commercial rooftops as well. After our solar discussion, we will get into battery sizing, both for off-grid and commercial batteries at a very high level. We will detail modeling building electrical demand a little bit further. Finally, we will conclude the program talking about digital electronic load control and how that can complement on-site renewables and battery storage.
Let's perform a PV watts example to determine how much energy a solar array will produce. We'll use PV watts to do this, a free and online resource published by the Department of Energy. The same data is by commercial design software for energy modeling, and so PV watts will tell you much environmental data about the project site under a close look, despite its basic appearance. PV watts makes it easy to get a good idea of how an unshaded solar array will produce its electricity for every hour of the day, every day of the year, based on local weather data. Input your address and system size to get started. I recommend performing a PV watts example using a 1 kilowatt solar array size to keep things simple. We can see that a 1 kilowatt solar array in Houston, Texas, facing due south at a 20-degree roof tilt angle will produce 1,400 kilowatt hours of energy per year. Summer days will produce more than winter days because the days are longer. More closely examine the input data, the roof tilt information button states that a common 512 roof tilt is at a 22-degree tilt angle. The solar array is facing 180 degrees azimuth, which is another way to say due south. A 90-degree angle would face due east. A 270-degree azimuth faces due west. All this can be modeled in PV watts. Now we know enough to run an experiment. Does a due west facing array perform any differently than a due south array? At a 512 roof pitch, the performance difference between solar arrays is 11%. Similarly, the performance difference between south and east is 11%. If the array is at a steeper tilt, for example at a 1212 roof pitch, which is a 45-degree tilt angle, the performance difference between due south and due east is 20%. Moving north up to Indianapolis, the performance difference between a 45-degree tilt at due south versus due east is 30%. In other words, the orientation of the solar array, or even the tilt angle, does impact array performance, but perhaps not as much as commonly thought. You can find solar arrays bolted 90 degrees down the sides of buildings, such as in New York City, where electricity is expensive and rooftops are cramped, or for off-grid power in Canada to avoid snowfall. Similarly, at a shallow tilt angle, the north side of the roof isn't off limits. So while east and west facing solar arrays are perfectly fine site selection spots, and even north facing solar arrays in some circumstances are acceptable, most solar in the northern hemisphere faces south. So as far as roof tilt goes, the array will follow the roof. Tilting up off the roof rarely makes sense, especially when the structure is considered. Steep angles will increase solar production, but also increase the installation and operating cost of the system, as the roof will no longer be walkable. If I know for my area, 1 kilowatt of rooftop solar will produce roughly 1,400 kilowatt hours per year, then 1 watt of solar will produce 1.4 kilowatt hours per year. That figure might be discounted 10 to 20% if the tilt angle is atypical, but for the most part, these calculations can be performed mentally in conversation to be later confirmed with a three-dimensional computer model and full shade analysis. But if 1 kilowatt array produces 1,400 kilowatt hours per year, a 5 kilowatt solar array will produce 7,000 kilowatt hours per year. A 5 kilowatt east facing array will produce 11% hours per year instead of 7. A home that uses 11,000 kilowatt hours of electricity a year, for that matter, will need around an 8 kilowatt solar array, give or take a few watts, to fully offset its energy use. Before leaving PV Watts, let's take a final close look. At the very end of the PV Watts calculation, the option is presented to download an hourly estimate. Additional site information is revealed, such as the amount of sunlight in the air and on the solar panel itself, as well as roof temperature, ambient temperature, wind speed, and more. All of these factors are being used, along with conservative assumptions about the solar panel itself, to produce an estimate that accounts for both sunny and cloudy days, the changing position of the sun in the sky throughout the day, performance losses due to heat, voltage drop, and system availability. The two major items PV Watts does not account for is shade or snow. So as far as shade goes, I recommend using commercial software to build a 3D model and perform shade analysis based on that. For snow, one simply needs to discount the winter season, perhaps entirely, if it can be expected that snow will sit atop the solar array for an extended period of time each year. The short of it is, by extracting this hourly data into a spreadsheet, the PV Watts data can be used as a foundation for more detailed designs, such as estimating off-grid battery bank capacity, quantifying the economics of selling electricity back to the utility, or evaluating alternate billing rate structures from the electric provider. Calculating solar payback is another essential industry skill. A great starting point is to calculate simple payback, which indicates how many years it will take for project expenses to be recovered. Let's assume you want a 10-year simple payback on your solar project. What should your budget be to achieve this goal? Let's assume the solar array has an effective generation rate of 10 cents per kilowatt hour. This number largely depends on how much the utility is required to purchase back solar power during the day, particularly if the customer does not have batteries. But for now, let's assume the customer earns 10 cents per kilowatt hour for solar production, regardless of whether it is sold back to the grid or used on site. From the PV watts section, the local production figure comes back into play. A common ratio for much of the United States is that 1 watt of solar will produce 1.4 kilowatt hours of energy per year. Multiplying 1.4 kilowatt hours per year by 10 cents per kilowatt hour lends a new payback metric, 14 cents per watt per year. So if the project needs a 10-year simple payback, then it should have a budget of $1.40 per watt per year to achieve that 10-year payback. The upfront tax credit is commonly included in simple payback calculations. Currently, the tax credit is 30%, set to drop to 26% in 2020 to 2021. After taking the 30% tax credit into account, the project budget should be no greater than $2 per watt to achieve a 10-year payback. According to 2019 solar installation pricing provided by Energy Sage, the average solar installation pricing is closer to $3 per watt. Applying a 30% tax credit, 1.4 kilowatt hours per year per watt production rate, and the 10 cents per kilowatt hour electric rate, the simple payback on a solar array installed at $3 per watt would be 15 years. In other words, simple payback is primarily a function of the production rate of the solar array and the electricity value that the solar array generates. PV watts can be used to determine how solar production value varies somewhat throughout the country. In Reno, Nevada, 1 watt of solar may produce 1.6 kilowatt hours per year. In Buffalo, New York, the same watt of solar on a roof produces closer to 1.2 kilowatt per hours per year, a 25% difference. But the price of electricity, as well as the utility buyback rate for solar power, vary much more widely across the country than the actual solar electric production itself. For this reason, it is safe to assume that the solar power market is primarily driven by the price of electricity, with the amount of sunlight in the air playing second fiddle. Because of the price of electricity, solar has a faster payback in New York City than in Houston, Texas. Despite Houston, Texas having cheaper solar installation costs and better solar production, the simple fact is that New York City electricity pricing costs 2 to 3 times as much as in Houston, Texas, allowing New York solar project economics to fare better despite the higher installation prices and lower system production. Now let's take a look at a typical residential project budget. Solar has dropped in price over the years, but cost reductions in the most recent years have been offset by increases in import tariffs. So based on Energy Sage pricing, even the 2015 and 2016 project budgets are still a realistic picture of what you can get today, including the import tariffs. In dark blue, the cost of the solar panel itself hovers between 40 cents per watt up to 60 cents per watt, including the price of the import tariff. The panel hard cost is about the same whether or not it's a residential, commercial, or utility scale panel. The markup on the solar panels that a distributor charges, which is more to residential markets than commercial, is modeled up here in gray, which we'll get to shortly. Here's the electrical balance of system material budget. I don't recommend cheaping out on electrical balance of system material, as there's some nice things you can add to a solar array to improve its quality beyond the panel or the inverter itself. A generator bypass switch at the top of the service panel can allow the homeowner to back up power capability for the whole house. Many potential solar owners are surprised to learn batteryless solar does not have the ability to provide power during a blackout, and even battery based systems typically do not supply the entire house during a blackout. Because battery prices are still dropping, the most cost effective solution for a solar owner who wants backup power capability can be to use a backup gas generator for now and wait for the price of batteries to drop further. Owners who want their systems looking clean and polished, which can be achieved with a little bit larger balance of system material budget for internal conduit runs, breakers, and subpanels instead of fuses and clunky disconnect switches. Modest upgrades will not increase the project cost exorbitantly, but will help the project obtain a nice polished look.
So how would one calculate the payback on a system installed at this budget? Again, PV watts is used to determine how many kilowatt hours of electricity a solar array will produce per year. Using a 1 kilowatt array as an example and divide by 1,000, most likely 1 watt of solar will produce between 1.3 and 1.5 kilowatt hours of solar production per year in your area. Next, identify the local net metering policy by visiting desireusa.org. Desire is a website of green energy incentives and policies at the local, state, and federal level. While visiting Desire, check for any state sales tax exemptions, but also use it as a starting point to determine the utility buyback regulations. A strong consumer net metering policy results in a one-for-one retail price exchange for the electricity the system will outflow onto the electric grid. In other words, every kilowatt hour the system outflows onto the grid will result in a credit of equal value to the kilowatt hours delivered by the electric provider over the course of the billing cycle. The most solar-friendly net metering policy results in the electricity consumed on-site versus the electricity sold back to the power company being valued the same. At the other end of the spectrum, without batteries, it is safe to assume that 2/3 of the system production will outflow onto the grid. After all, society uses electricity 24/7, whereas solar only produces between the morning and evening, with most of its production occurring in the middle of the day. So if the goal is a solar array that offsets 100% of a facility's energy use, roughly 2/3 of that production will either need to be stored in a battery or sold back to the utility. With so much production needing to be bought back by the utility if the solar array lacks batteries, it is a good idea to contact the utility to confirm the net metering policy before proceeding any further with the project. Likewise, it is necessary to examine the electric bill to back out any fixed charges from the bill before determining the effective generation rate of the solar array. In any event, the effective generation rate of the solar array is either 100% of the utility's energy pricing, assuming a solar-friendly net metering policy, or on the other end of the spectrum, up to 2/3 of the solar array production could be discounted by as much as 80%, such as if the utility buys back for the federally mandated minimum an amount known as avoided cost. Once the local buyback policies are determined, the effective energy rate of the solar array can be quantified in $1 per kilowatt hour unit. Now, payback can be calculated.
The project budget divided by the project size to get a dollar per watt figure. Solar production is measured in kilowatt hours per watt per year, and the effective generation rate is billed in dollars per kilowatt hour. So combining these figures together will give you a simple payback measured in years. Lastly, check the value of any tax credits or incentives. The federal tax credit for solar, which includes batteries, can vary between 10 to 30% depending on governmental change winds. Sales tax exemptions can take a year or more off of system payback, assuming a $2.51 per watt installation budget. A state sales tax exemption could be worth 16 cents per watt. A federal tax credit of 26%, a generation rate of 1.3 kilowatt hours per watt per year, and an effective generation rate of 10 cents per kilowatt hour. The simple payback on this solar array would be 13 and a half years. Section 3, Array Layout. At a very high level, solar array layouts are an exercise of how many rectangles can fit into the larger rectangle or surface area, but a small amount of shade can be managed. A good rule of thumb is to completely eliminate any solar production from the PV watts estimate for the time that the solar array is shaded. I perform shade analysis using commercial solar design software because the market-leading software companies integrate LiDAR data into their design software package, making three-dimensional shade analysis accurate and easy. This is the same data that Google Earth uses to make its 3D models of trees and buildings in Google Earth. However, solar installers may also use specialized field survey tools to calculate shade loss percentages, or even basic trigonometry to get a rough idea of what the shade conditions on site will be, at least the worst ones to be avoided. It should be obvious that a good solar job site is one with large open surface areas with access to sunlight. While partial shading can be designed around, the whole point of solar is not to be in the shade. In the PV watts section, we learned that an east-facing solar array will produce 15 to 30% less than a south-facing array, depending on the tilt angle of the roof. Let's expand that philosophy to also consider the north side of the roof. A due north-facing array in Indianapolis, Indiana, at a 45-degree tilt angle produces 55% less than its south-facing counterpart. Combine the two roof surfaces together for a total unshaded yield of 155%. What's interesting is that an east and west facing roof would produce 77% less than their south facing counterpart, and if they were combined together, the total unshaded yield would be 154%. In other words, if one covered the entire rooftop of a building with solar panels, roughly the same amount of energy would be harvested from the roof, regardless of whether or not the building is oriented north, south, east, or west. Southern roof surfaces are certainly more desirable than east or west facing roof surfaces, and north facing roof surfaces should be considered last, and only if there's project budget or an electric bill remaining. But consider economies of scale. Upgrading a residential project from a 20 solar panel project to a 40 solar panel project will not double the design, nor labor, nor balance of system material cost, nor would it double the permit fees, engineering cost, or sales commissions. This is called economies of scale. The larger the solar project gets, the lower the price comes per watt. In a region with an average installation price of $3 per watt, a small residential project might cost $5 per watt, and a large residential project could cost $2.50 per watt. By increasing the project size, the economies of scale can drop the cost of the project per unit more quickly than the performance loss resulting from moving the project onto less than ideal roof surfaces. The complexity of the roof is as important as the roof tilt or orientation. A walkable roof maxes out at a 512 roof pitch. The steeper the roof, as well as the height of the roof, as well as the type of roof, can substantially increase the project complexity and cost. As a solar installer, I want to select a couple of roof surfaces with access to sunlight. The orientation of the roof is only one consideration. In fact, in a southern climate with a shallow roof tilt, I might cover the entire rooftop if the budget and electric bill allows. Solar is an outdoor rated electrical device designed to withstand the elements. In a catastrophic hailstorm, a solar array is more likely to save the insurer money by avoiding a total roof replacement rather than cost them money with a solar array replacement. But that assumes the solar array protects the entire roof. Perhaps the greatest conflict in solar design is that between installers and architects. Solar wants a large and boring roof, whereas an architect wants a complex roof broken into little sections. Rather than list the nuances of every solar design and optimization theory, let's keep it simple by suggesting a good residential solar project consists of at least one pallet of solar panels covering the best 2 or 3 roof surfaces. Then, if additional budget allows, more panels on less optimal roof surfaces can be considered. Likewise, try to avoid placing just a couple of solar panels off by themselves on a small roof surface, regardless of how ideal the orientation is, simply because of installation complexity. A pallet of solar panels is almost always between 20 and 30 solar panels multiplied by roughly 3 1/3 feet wide by 5 1/3 feet tall. So good roof surfaces that are rather large or boring, regardless of orientation, are good solar roof surfaces. Similarly, an east-west roof can be as viable as a north-south roof in terms of project location. I don't even mind a system which produces more electricity than the building consumes. You can always find a use for more electricity, such as reduced reliance on gas or wood heat in the winter. One of the more important decisions of solar design is considering rooftop accessibility, as slanted roofs are not designed to be accessible places. But with a solar array located on the roof, that roof surface will inevitably need someone back up on it for array servicing at some point in the near or distant future. It is possible to cover an entire slanted roof from edge to edge with solar panels and maintain compliance with international building and residential building codes. It is also common for local authorities, such as fire departments, to add additional stipulations, such as a common 3-foot offset from the sides and top of the roof requirement for solar array layouts. The main concern is that a building need an exhaust plan to ventilate smoke from attic spaces and lofted ceilings in the event of a fire. So if a sleek edge to edge modern look of a residential solar home is desired, know that it is possible to obtain exemptions from these 3-foot offset rules on slanted roofs, even when mandated locally, if other kinds of ventilation systems are planned in those spaces. Flat roofs, such as commercial rooftops, have their own rules and regulations, which are commonly staying 6 foot from the edge of the roof. That is simply a good practice to discourage maintenance workers from getting too close to the edge of a building, although it can make solar on top of tall, skinny buildings a little bit more difficult to locate. At any rate, there are valid reasons to stay off the edge of the roof with a solar array. Wind speed is greatest at corners and at the edges of the roof, such that the solar array will result in more force on the roof truss during extreme wind if installed on the edges of the roof. The roof itself may overhang the structural wall, and so the attachments on the interior of the roof will be stronger if kept to the inside of the structural wall. The roof cap or ridge may need additional space for servicing. A design change in the field may be more easy to implement if there's some empty space remaining on the roof. Lastly, as an installer, there's a big difference between climbing onto a rooftop to access a troublesome solar panel as opposed to disassembling the entire solar array to clear a path on the roof to get to where the trouble is located. Now, I love the solar bling bling look that takes a normal boring roof and turns it into something special. But the more accessible the roof is, the better. In fact, if the solar array is being installed on a rooftop that is wholly inaccessible, that is a good time to spend additional money on quality and top shelf components as well as labor to ensure that the trips back up to that rooftop are infrequent. A pre-built roof is not intended to be a construction site. Clearances around skylights or other roof-mounted equipment become walkways for solar construction workers during construction. When leaks do occur, it's usually in those walkable areas rather than within the array perimeter itself. Shingles in particular do not take much wear and tear, but a well-built solar array should extend the life of the roof. The shingles are primarily degraded by exposure to sunlight, so shading a shingle will increase its life. But plan the project with the intent to reduce the total amount of time spent on the rooftop as much as possible. Pre-assemble as much practical on the ground to reduce the time spent up on the roof itself. Let's end the array layout section with an interesting energy metric. The Department of Energy pegs commercial average electric use being at 14 kilowatt hours per square foot. And let's assume it's less than that for residential. How many kilowatt hours per square foot does a solar panel produce in a year? We've already provided enough information in this program for you to calculate that. If a solar panel is 3 1/3 feet by 5 1/3 feet, and also assume it's a typical 300 watt solar panel, let's assume 1 watt of solar produces about 1.3 kilowatt hours per year. So multiply 300 watts by 1.3 watts per kilowatt hour per year to get about 400 kilowatt hours per year. Dividing by 18 square feet results in approximately 21 kilowatt hours per square foot per year produced by a solar panel. on top of a building that only consumes 14 kilowatt hours per square foot per year. Of course, every building's energy use will be different and site conditions can impact solar production, but the point is that solar panels can produce more energy per square foot than what an average building uses per square foot, and by a healthy margin. This implies that a solar array can produce all of a building's energy needs by harvesting that energy from the roof, even without covering the entire structure to do so, at least for a one-story building. On a two-story building, it is still possible to generate 100% energy offset when all sides of the roof are used, which is possible if the roof has a walkable tilt angle. Of course, the taller and skinnier the building is, the harder it will be to take that building completely off grid. So at this point, a design algorithm emerges for selecting the ideal roof surface for planting a solar array on the roof. Start by identifying large, open, sunny areas on the rooftop. South-facing surfaces are best, but anywhere between due east and due west is just fine. If the roof has a 512 pitch or less, consider the north side of the roof as well. In other words, if the rooftop is walkable, the north side of the rooftop should still be considered as a potential site. If the project skips some of the design phase, such as not being reviewed by a structural engineer, nor having a third-party inspector get into the attic to verify the lag bolts hitting the rafters, nor checking with the local jurisdiction to see if there are local roof offset requirements, then it is safe to maintain a 3-foot offset from the roof ridge and roof rakes, which are the tops and sides of the roof. Even a slightly larger offset has benefit. A 4-foot offset gives the installation crew even more flexibility if encountering unforeseen roof obstacles or structural issues. The further away from the roof edge the solar array is mounted, the easier it is for the loading on the roof. That extra space is useful for solar array maintenance, so there are many reasons not to put the solar array all the way to the sides or top of the rooftop. The bottom edge of the roof is a different case. I don't want workers anywhere near the edge of the rooftop, so by filling the bottom region of the roof up with solar, I might physically prevent a worker from walking along the edge of the roof. It's also best for snow and rainwater runoff, so a good solar array will start the solar panels a couple inches from the bottom edge of the roof, such that torrential rain will not overshoot the gutters, and then continuously run the solar array up to about 3 to 4 feet from the top of the roof. Personally, I would only bother with roof surfaces that can fit 8 solar panels or more, such that the installation crew can work efficiently and a good installation price can be obtained. A pallet of solar panels is between 20 and 30 panels, and a good-sized residential project can be 2 pallets, which is about 15 kilowatts. Of course, more difficult installations are possible and occur regularly, but solar panels do require some maintenance access. So failure in the safety electronics could take a solar panel offline until someone gets up on the roof and puts hands on it. A long period of time without rain could result in dust and pollen accumulation on the array surface for cleaning. Proximity to a dirt road can do the same. So rooftop access is useful simply for cleaning the solar array before any other maintenance issues are considered. In other words, when planning a solar array layout, identify large, open, accessible roof surfaces and fill them up with solar panels in a maintenance-friendly layout before moving on to less ideal but still large surfaces, so long as there is a budget and electric bill remaining.
Let's start by going through the steps of what's needed to prepare a residential solar project for permitting. There's a variety of software available to speed up this process, and one of my favorites for small residential projects is Solar Design Tool. A good solar project should not be installed in an area that has significant shading. And partial shading is, essentially resolved through module level panel electronics. So without more further ado, let's get into the design example. So here I am in Solar Design Tool. I create a new project and click go, and then I enter in the site information. Already I can tell that some solar production data is keyed into the same database as PV watts used to develop its energy estimate. So the same weather stations that PV watts keys into, solar design software keys into. Already, Solar Design Tool is asking for some advanced project details, which is why I love this software so much. Although Solar Design Tool has its limitations, it is uniquely focused on creating a final project document that is ready to be dropped off at the local permit office. As such, it's worthwhile to provide it with things like meter numbers and electric service panel information, such that the permit document generated is sufficiently detailed. This kind of project information can only be determined through on-site inspection. So if attempting to perform the design 100% remotely, it's useful to ask the site owner to take enough photographs to provide these details. Here, Solar Design Tool is asking for subpanel information. A subpanel might be used if there are multiple inverters which need to be tied into a single point at the main service panel. While Solar Design Tool has many different configuration options, it may not have the exact configuration for a particular job site. So in many cases, it will generate a permit-ready document, but sometimes minor changes are necessary to be completed in an external CAD software such as AutoCAD or DraftSite. So if you don't know some of these terms, such as the difference between a top-fed service panel or a center-fed service panel or a main lug only service panel as opposed to having a main breaker, then you might not be competent enough to perform this level of solar design detail, at which point you should consult with an electrician to complete these steps. Other project information is inputted, some which is technical. This can be omitted, but there is no reason why this level of detail cannot be established at the front end of the project. Then pulling this information together, such as knowing who your local authority having jurisdiction is or what version of National Electric Code you're on, it allows for a more successful project altogether. Site conditions inputted include local building code and wind speed, surrounding terrain, which will then be called out in the final permit documents. This information is used when using manufacturer provided sizing tools, such as racking sizing software or even inverter circuit sizing software. So at this point in the project design process, this information should already be known. Now the next step is it's asking us to draw out the rooftop. There's a few options to do this, ranging from simply inputting the dimensions of the installed area to tracing over an aerial image, like overhead map, to actually buying a mapping service to do the heavy lifting for you. So depending on what you're already purchasing, you may already have a 3D model. But the most common premise for a starting point for solar design software is that the array will be developed by tracing over a satellite image. So later we will explore some other options where satellite images found on Google Maps may be insufficient. But at any rate, here's the job site. It's immediately apparent that there is a large southern oriented unshaded roof surface uh, that is a ideal roof surface for a solar project, although it might be worthwhile to consider solar on the west facing roof surface and even on the north facing roof surface depending on the roof tilt. um, Other kinds of solar design software are better at determining the roof tilt than Solar Design Tool. Even so, toggling the street view and the tilt view can provide enough visual detail to attempt a guess at the roof tilt, as well as identify other rooftop objects. Now it's time to define the area of the southern roof, which is a simple matter of pointing and clicking around the roof surface with a double click when complete. The orientation of the roof is then specified. We are then prompted to enter the roof pitch. So this process is then repeated for all the roof surfaces. So how accurate do these roof areas need to be? It depends. Many jurisdictions require a 3 foot offset from the roof ridges and rakes, which are the sides and the tops of the roof. For structural and accessibility reasons, it is even better to stay 4 feet off the sides and off the top of the roof. This would give the installation a nice margin of error by reducing the need for careful site layouts. However, roofs with more substantial penetrations may require more accurate planning. Um, for most solar design software, the procedure is to define the usable roof areas first and then add on any obstructions second. So here we've mapped out different obstructions on the rooftop. These pre-existing holes in the roof, chimneys, plumbing vents, valleys that are shingled over or flashed together. These pre-existing holes uh, become common leak hazards after the solar array is complete. This is because most workers on the roof are stepping on these locations. A risk that is increased, particularly with a compact array design. At any rate, the clearance areas around a chimney, around a plumbing vent, or around a roof cap can become walkways, and they might need to be repaired at some point in the future. So it's best to allow for some clearance around these obstacles, even when the clearance is not required. There are exceptions. An ugly solar array does not add as much value to a home as a pretty solar array. So if the array's look is significantly improved by putting a solar panel a little bit closer to that chimney, it may be acceptable so long as the client understands the design decision. In any event, clearance space around the chimney is more important than clearance space around a plumbing vent, and staying clear of these obstacles kind of removes the need for nuance. So it's time to locate the equipment. Solar Design Tool is asking the designer to locate the main service panel, utility meter, as well as any sub panel or disconnect switches. Google Street View is your friend here, as it tells you, where the meter location is without having to step foot on the site. Of course, this information can be picked up in a site evaluation or by simply chatting with the client. solar design tool is asking for the building's least horizontal dimension, useful for engineers in determining wind load, although this typically is resolved from over engineering the racking or offsetting the array from the roof edges to mitigate wind load. Google Earth, with its built in ruler tool, can be useful in quickly measuring this dimension. In this case, the building measures 50 feet wide. These are roof and rafter questions, which again is information supplied via a site visit. But anyway, we've sketched our roof, and now we are presented with three defined roof areas to lay modules onto. This menu is similar to using a manufacturer's string sizing tool, combined with an array layout generator. It's not as nuanced as other solar design softwares. So sometimes it's best to do the shade analysis and array layout in a different solar design software before importing the design or remodeling the design within Solar Design Tool. After selecting your module and your inverter, you're presented with your circuit configurations. This is a microinverter design, and the microinverters, per their specification sheets, are limited to 17 modules per circuit for this particular module on this particular inverter, and it gives us different branch circuit configurations. The north roof gets 17 module circuits and very long, even circuits. The south roof, the circuits are kind of divided up to make the installer's job easy. So in this example, I'm taking a 320 watt black on black 60 cell module combined with a DC optimizer inverter system. Taking a quick look at my array layout, I can see that 31 modules fit on the south side of the rooftop. Um, I'm a big fan of ordering by the pallet. And so here we have in a portrait orientation, I can fit 31 modules on the roof. Or if I use a landscape orientation, I can fit 29 modules on the rooftop. That's not the end of the story. I'm a big fan of ordering by the pallet. So I find that ordering pallet quantities of solar is the best way to work the supply chain. Likewise, portrait mounting makes quick and easy work on a shingle roof. Because of how the rafters and purlins are laid out on a metal roof, it can be the opposite way. And so in Australia, they have a lot of metal roofs. They do a lot of landscape orientation. In the United States, we have a lot of shingle roofs. We do a lot of portrait orientation. In some cases, landscape can be the better choice. Aesthetics can fit into it well. But for this particular solar panel, looking at the spec sheet, one pallet of panels comes with 25 solar panels. So if my client only has budget for one pallet of solar panels, I can easily fit 25 solar panels on the south side of the roof, regardless of whether or not it's in a portrait or landscape orientation. Here's a project example that would be a very easy and not too ugly of an install, where I can fit 25 solar panels on the south side of the rooftop. Um, and so if I'm just going for a low budget, fast, easy one pallet installation, this is probably the array layout I would end up with. So I can fit 33 solar modules on the roof, maybe 32. I can fit more modules on the rooftop in a different orientation. And so if I wanted a larger system, if I was doing a two pallet solar design. Um, I'll look at the south side and the west side of the roof uh, in a more compact frame to fit everything in a aesthetic manner. Although it would be a more difficult installation. An installer might, in a more active market, may design to have this kind of best fit system to the roof. In a cheaper market, with lower project costs, they might go for an easier solution that covers, all three surfaces of the rooftop. And, that empty space allows you to make some minor adjustments for array aesthetic considerations and maintain the portrait orientation that makes for an easy install. Um, aesthetics and ease of installation are also important in your array layout, as well as how many solar modules can you fit on the rooftop.